Hello and welcome to this new video where we talk about math and physics on the board. Now, in this video, what we are going to do is basically go back to a result we've derived on the board, which has to do with so-called Jacobian transformation rule for the volume form. And then we are going to see how we can interpret what's going on geometrically. Right, so let's start with the basics. So the way I've actually defined integration by using exterior calculus was definitional and purely algebraic. Okay, so essentially I was using exterior calculus and I simply stated that there is a general theorem of like fundamental theorem, if you will, of calculus that applies in the context of exterior calculus. And this has the effect to give rise to this so-called Jacobian transformation rule when you look at the volume form. So if you've got a space in k dimensions, then that's going to be uh, basically the wedge product of k differentials, and that's going to be what is called the volume form. Often this is taken so that you've got this initial volume form which corresponds to orthogonal, if you've got a corresponding scalar product, orthogonal directions. But this doesn't need to be the case. This formula would work whatever you start from. But the bottom line is that if you've got a certain system of coordinates and you've got here an actual k, like you've got multiple wedge products of these k blades or forms, then you end up with this formula for the new coordinate system or the new set of variables y. Okay, so y1 to yk. And these double bars signify that this is a determinant of a matrix object that is J, called the Jacobian matrix. And this Jacobian matrix is just this object here, where you can kind of complete in all the other case, but where you've got here the gradient, if you will, of x1, here's the gradient of x2, and so on, relative to the new variables yk. Okay, so that's kind of the starting point. And in this particular thing, there is nothing kind of visual or geometrical. It's basically just using the algebra. And here we basically take the determinant of some kind of differential object. So that's kind of it. Now, the goal is to remember that in the very first video we did on exterior algebra, even before talking about exterior calculus, essentially we talked about having, let's say, one vectors and interpreting these one vectors as being vectors. So vectors meaning segments with a direction. So that's really a geometrical object in that sense. And so here, for example, I represent alpha. Now you can imagine alpha with some arrow here and beta with some arrow as well. So it's a segment with some direction that you're going to choose. Now, the new thing in exterior algebra is that you can also represent, rather than simply lines, sums of lines and stuff like that, you can also represent actual higher order geometrical forms. And so here this is an actual parallelogram that is made of alpha and beta. And so alpha wedge beta actually represents the entirety of the parallelogram. So that's the parallelogram made out of alpha and beta. Okay, so that's kind of the idea. It represents this particular parallelogram. And so what we can do, therefore, is try to see how does that apply to the Jacobian formula. So to illustrate this, let's have a look at a case in 2D. So therefore, the volume form is going to be two-dimensional. And in that case, I'm just, for the sake of illustration, suggesting that we've got a map. So we change the coordinate system from xy, let's say, to a new one that is called u, which is ax plus by, where a and b are constant factors, and then v of xy is y itself. Okay, so essentially that's it. And what I want to see is how this is going to change basically the expression or the shape rather that we are looking at to integrate. Okay, and so dx dy is basically the fundamental element of integration. and this is going to be interpreted here as orthogonal kind of direction, x and y, and so that's basically a rectangle, okay, with dx and dy here. Now, if I put du here, I'm going to have that this is a dx plus b dy, and then this is wedge dy. So what I can do is actually say, well, I can just plot this a dx plus b dy and see what I get. And so what is going to be left is that I can interpret this as a sort of vector, in the same way that here I've interpreted that as a sort of segment, and so here as well a segment. So I'm going to do the same here, and this is going to be a vector that is going to have some angle, okay? Now the way I'm going to do this is first I'm going to actually do the dy part, okay? And then I'm actually plotting the rest, okay? And so here what I've plotted is the dy is still remaining the same, but then this one now is actually du. And so that's a dx plus b dy. Now, one of the things you can see is that the degree to which this thing is tilted depends on a, okay? And so here, for example, there is some value of a, but what we can see is that if I decrease a, okay, if I decrease a, then I'm going to end up with something like this. So let's keep about this length. And then I'm going to get, so I need to do something maybe like this. And that's going to be much more kind of slanted like this. And what's going to happen is that as a tends to 0, then the area of this is going to be 0. Okay? And so that's why, of course, if you want to relate it to the area of that rectangle, then of course you need to make sure that you put a correction factor which has to do with a. So here we decrease a, and eventually this thing is going to tend to 0 over time. Now, one way we can see that is because the wedge algebra says that this is a dx wedge dy, and then plus b dy wedge dy. But you remember that dy wedge dy is actually equal to 0. So what we have left is simply a dx wedge dy. So the wedge product, yes, indeed, corresponds to the actual, parallelogram that you want to look at. But then when you expand that again upon x and y, you're going to express that as a sort of sum over these small rectangles, which are going to have the same area and so on and so forth. And you see here that there is this a. So if a basically tends to 0, so does du wedge dv, okay? And so again, that's why when you want to relate it to dx dy, you need to compensate by the, the skewness and the fact that the parallelogram is flatter and flatter, and so you need to account for that when you transform to actually get the same integral, okay? If you don't do that, if you don't put this Jacobian stuff, then essentially the slanting of this new parallelogram is going to bias your integration. Okay, so I hope this clarifies a little bit from at least a graphical and visual standpoint this subtle aspect of these Jacobian transformations. If you've got any questions or comments, please do let me know in the comment section. Otherwise, see you in the next video.